Bismillahirrahmanirrahim. In a MOSFET metal oxide semiconductor field effect transistor, the inversion layer forms when a sufficient high gate to source voltage, which is called VGS, is applied, and which attract minority carrier to the surface of the semiconductor near the oxide layer, creating a conductive channel between the drain and source terminal. This process is very crucial for MOSFET operation as it allows the device to switch between conducting and as well as non-conducting states. Initially, the MOSFET substrate, typically P-type MOSFET for NMOS semiconductor field effect transistor, has abundance of majority carrier which are hole and very few minority carrier as electron. When a positive voltage is applied to the gate in case of NMOS, the electric field generates across the thin insulating oxide layer, pushing the majority carriers hole away from the surface of the p-type substrate and create a depletion layer, as like that here, where the carrier concentration is very low. Now look at the figure A. No gate voltage is applied, and the field is generated in the insulating layer is nearly negligible and practically no ID. Current is shown in the IDS and VDS current, and it is no current is passing through the drain source voltage. Now look at the figure B, where source voltage Vs is equal to 0 because the source voltage, the source is connected to the ground or zero potential, and drain current Vd is greater than 0 volt. Small voltage as compared to 0, and its more positive voltage is applied to the gate, and so that gate VGS is greater than threshold voltage. The gate voltage is greater than VT, as we discussed earlier. A threshold voltage is defined as the minimum voltage required for the formation of inversion layer, or sometimes it is called channel layer. So here meaning is that inversion layer or channel layer has formed. The current through the drain is small because our VD is very small, and as here, and that indicating that MOSFET is not fully in the saturation or high conducting state. In this state, the MOSFET operate in the linear or triode region, and a small resulting drain current. The transistor is partially on and the gate voltage VGS is greater than VT, but it is not operating as the full strength or the saturation stage as we will see in figure C and D. This condition is typically in analog circuits where the MOSFET operate as a variable resistor or in early stage of the transistor operation before high drain current are being applied. Now look at figure C. The formation of channel is taking place as the gate voltage Vg exceeds the threshold voltage. An inversion layer, which is in conductive nature, forms between the source and drain. This allows current flow from drain to source as ID is greater than 0, and you can see the between graph between ID and VDS. As the drain current increases VD, the electric field between the drain and source puts more current through the channel. In this region, the current ID increase linearly with VD. The entire channel is present from the source to the drain. Certain drain voltage called the pinch of voltage, this voltage. And this voltage where the difference between the gate drain become equal to the threshold voltage. In other words, Vg minus Vt is equal to Vt. Vg minus Vt is equal to Vt. This means that near the drain, near the drain, the channel potential just reached the threshold voltage. Now question is arises, what happened at pinch off? The channel near the drain become depleted and no further increase in the drain current can enhance the channel near the drain current. And channel is narrowing. Although the channel is still connected at the source and it began to pinch off at the drain side. Beyond this point, any further increase in drain voltage VD does not significantly increase the drain current. Now look at the figure D where VDS is continuously increasing and we will observe saturation region which is called as a post pinch off. Once the transistor reaches the pinch off point, it enters into the saturation region. Now the drain current becomes relatively constant and primarily determined by the gate source voltage, not the drain voltage. This relationship in saturation mode it can be defined by a different mathematical equation, but very simple way. ID is equal to mu and C of which is a capacitance of the oxide multiplied by W over L and multiplied by VGS minus VT square, where W is the channel width, L is the channel length, and mu n is the electron mobility because our channel is an N-type channel and our MOSFET is an N MOSFET. Now there is a misconception about current stop. Even though the channel is pitch off near the drain and current does not stop, current is still passing through here. It is a constant. Instead, the electric field between the source and drain pull electron through the pinch off voltage, allowing current ID to continuously flowing through here. But it is a constant value. It cannot increase with the increasing the device VD drain voltage here. Thank you.